Welcome to the 25th lecture. We are studying stochastic processes. In last lecture, we studied birth-death processes under Markov process, birth-death process under Markov processes. Today, we'll study uh, another kind of Markov process, which is random walk with reflecting barriers. The chain, Markov chain that governs this process is very similar to the Markov chain that we studied for birth-death process in lecture 24. Right. Let's see what kind of chain governs this random walk process with reflecting barriers. So this chain is very much like a birth-death process that we studied in last lecture, with the difference that there is no arrow that is that initiates and lands on the same state, except for the barriers. Barriers means the first state and the last state, right? So in addition to first and last state, there is no self transition arrow throughout the chain, right? We have only the birth probabilities. This means that we have an option of having a burst probability that takes us to the state from state I takes us to state I plus 1, and the death probability, which is 1 minus b, because we don't have any other option, right? So that takes us from state I to state I minus 1. But if we are at the first state, then we have to land back on the same state with probability 1 minus b. And if we are on the final state, we have to land back on the same state with probability b. Right. So all forward probabilities in short are b, and reverse probabilities are 1 minus b. Right, but the barriers on both sides, state 1 and state M, are reflecting. Right. So 1 and M are state 1 and state M are reflecting barriers. This I have told already. Right. So now we want to find out the steady state probabilities for all states. Let's find it for state number 1. State number 1. And if we want to compute it for state number 1, we come up with probability pi 2. But let's start it with pi 1. We know with this recursion based formula, we have used it a large number of times in our previous lectures. So pi 1, let's compute pi 1 using the same recursion based formula that we studied for 5 lectures before. And if we expand this and put these transition probabilities from this Markov chain, we we reach to a value. Pi 2 is b over 1 minus b times pi 1, right? And then we will repeat this process for state number 2 for this state. And we know that there are only 2 arrows going out of it and only 2 arrows landing on it. So we'll start with the same. We'll start with the same recursion based formula for state 2. and and that will and expanding this will take us to a point where we have pi 2 on the left hand side, and on the right hand side we have pi 1, pi 3, and then we can substitute the value of pi 2 from here. pi 2 is b over 1 minus b times pi 1. So if we substitute the value here, we have this one equation in terms of pi 3 and pi 1. Solving it further, okay, takes us to this b over 1 minus b with whole square times pi 1. So in this equation, let's call it equation number 2. For this equation number 2, we have written pi 3 in terms of pi 1. But in equation number 1, we wrote pi 2 in terms of pi 1. So we can write the probability of every other state except state number 1 in terms of the long-term or steady state probability of state number 1, I mean pi 1. So every long-term probability or steady state probability for any state I can be written as b over 1 minus b to the I minus 1 times pi 1. And this is true for I 1, 2, 3. In fact, it's also true for I is equal to 1, because if you put pi 1, this whole stuff becomes b over 1 minus b to the 0, 1. So pi 1 becomes equal to pi 1. So it's true for I is equal to 1, 2. So 1 to m for all states in for all state in the state space of this Markov chain. Right. So it's a very general formula, but 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 we have m minus one equations. M minus one equations. If m states, we have m minus one equations, but we have m variables. So we need one more equation, one more linear equation. So we need one more linear equation to find all values of pi's, the long-term probabilities. For that, of course, we'll get help from normalization equation that tells us that the sum of probabilities, long-term probabilities, or steady state probabilities of all states is equal to of 1. So, and then using this as the last equation, as the mth equation, we can solve for for all pi i's, for all pi i's. Right. So that's all for this lecture. In the upcoming lecture, we will study some more interesting information about about Markov chains and Markov processes. Thank you.